So this is the second lecture of our joint course with Sergey. And so for me, this is the first lecture. So I write lecture 1, almost complex structures. Let us consider the simplest case of complex structures on a real vector space. So complex structures on a vector space. Let V be a real vector space of dimension 2n. A linear map J, V to V, so a linear map is called a complex structure on V if simply it satisfies this condition, G square is equal to negative identity. This is canonical property of complex structures. Sometimes I will refer such complex structures as linear complex structures in order to stress that this is just a linear map of a real vector space to itself, and so on. So typical example, and of course the most important example, is given by the space Rn. And so first example considered in the talk of Sergey. So if our space is R2, then we can consider the standard complex structure, which is the linear map with this matrix. Well, with some abuse of notation, of course, I identify linear maps and the matrices because here we have canonical system of coordinates. And so sometimes, in order to stress that this is in real dimension 2, well, I will write like this. But sometimes I also drop this. So this is very typical example of a complex structure. We can increase, of course, the dimensions. So if we consider now V as R2n, then we can define the standard complex structure on the space. It depends, in fact, a little bit how you write coordinates in the space. If you write the coordinates like this, and then we can write the standard structure something like this. You write this matrix on the diagonal. Well, another way is to write the coordinates like this, and then the matrix of the G standard structure will be something like this. This is two possible ways to generalize this formula for higher dimension. Well, so why these examples are important? Well, because first of all, if you use this complex structure, then we can canonically identify R2n with the structure with Cn equipped with the standard complex structure. This is very classical identification. You define this multiplication of a real vector by I like this. And R2n becomes a complex vector space of dimension n. And in general, when you have a complex structure on a real vector space, then using a similar formula, you can view this as a complex vector space of dimension n, and so on. Well, so the importance of this example comes from the following basic linear algebra proposition. Suppose that you have any vector space with a complex structure, then we have this, then there exists a map phi from R to N to V, which is linear isomorphism, such that J is equal to phi J standard phi -1. In other words, J is the direct image of the standard structure. So every complex structure is conjugated to the standard one on any real vector space. And this is a fundamental fact for the author. This is elementary linear algebra, which allows to prove it. Well, so this is important basic result. Of course, you can find the proof in any book of linear algebra. So some terminology. So if you have now a vector space with prescribed, with chosen fixed complex structure, then you can consider some subspaces in this vector space. So subspaces. Well, there are two important classes of subspaces. The first class is formed by J-complex subspaces. Just complex subspaces when J is prescribed in norm. So L subspace of V, real subspace of V, is called J complex if for every vector V of L, J V again belongs to L. In other words, if L is invariant under the action of the complex structure. This is the first important class of subspaces. And the second class is in some sense opposite, so totally real subspaces. So this is some subspace is totally real if the intersection of L with JL is equal to the origin. So in this situation, the intersection L with GL is the maximal possible, which is equal to L. In this situation, this is the minimal possible intersection, which is equal to the just to the origin. So typical examples are, for instance, if you are in Cn, you can think about, well, any zero sets of complex linear form, usual complex subspace, something like the ZG is equal to 0 in standard coordinates. In this case, you can think about something Rn in Cn, typical example of a totally real subspace. Well, a last remark, every complex space when you have fixed structure J, then you always have a canonical orientation. So canonical orientation is also very well known. Canonical orientation of Vj. Just take any complex basis on V of V, so a complex basis, so C basis, and then you can consider this system of vectors. It is easy to show that this is a real basis, and all these bases have the same orientation, which is independent of the choice of this complex basis, and so on, so on, so on. So it defines the canonical orientation on the space with complex structure. Okay, so this is linear algebra. So now almost complex manifolds. Suppose that you have a manifold M, which is real, of dimension 2n. Well, very smooth. If it is not mentioned, all manifold structures will be of class C infinity. When it will be important, I will precise the smoothness. So of class C infinity, if it is not prescribed. But of course, you can consider it's for very low smoothness, like C1, CK alpha in Hilbert classes, and so on, so on. So let it be like this. So now consider a tensor field on M. So a tensor field J of type 1, 1. So this means simply that this is a map which for every point P from M, this map associates G of P, which is a linear map of the tangent space to M at point P to itself. So this is, so G of P is a linear map to this, and we suppose that this linear map is a complex structure in that sense. So this is equal to negative identity. So, and this is true for all point P of M. And so when you have such a J, J is called an almost complex structure on M. So J is an almost complex structure on M. And if you have fixed an almost complex structure, then this couple Mj is called an almost complex manifold. Well, the definition, which is important. Suppose that you have two almost complex manifolds, M prime, J prime, and Mj. What is a what is a just holomorphic map between these manifolds? So a map F between two almost complex manifolds is called well, formally I have to say J prime, J holomorphic. But often when structures are prescribed and known and we do not move them, I will drop this J prime, J. But formally this is like this. This map is called J prime, J holomorphic if J df is equal to df J prime. So the differential, the tangent map of F commutes with almost complex structures in the source manifold and in the target manifold. Okay. Of course, if we impose this condition, at least we suppose that df exists in some sense. So, well, the natural category for this definition is that we suppose, for instance, that f is of class C1. Okay? But in principle, this definition can be written for manifolds with low regularity. You can, for instance, think about derivatives in Sobolev sense and so on. But at least you need something. You need some initial regularity for your map. It is not totally arbitrary. Okay? So in some sense, you need to. I intentionally do not precise the class of regularity. It will not be important for us. But when it will be important, I will precise. Okay, but you need some. So let it be C1 for a moment. Okay, so this definition is not very usual, maybe for people who study the traditional classical complex analysis, but in fact there are nothing very complicated. So example, suppose that your first manifold is just the space, well, Cn with standard structure. The second also Cm with the standard structure. Then this definition is equivalent to the classical definition that every component of your map satisfies the usual system of Cauchy-Riemann equations, which will be written in the real form. If you view this map as map between R2n to R2m, and you write this relation in coordinates, then you will exactly obtain the classical Cauchy-Riemann equations for every component. So it is very easy to prove. And of course, I leave it as an exercise. Okay. Well, so what are examples of almost complex manifolds? Of course, so examples. The first basic example, of course, is if you consider D a domain in Cn and J is the standard structure of Cn, then dj is an almost complex manifold. It's obviously to check it. More generally, in fact, more generally, every complex manifold is almost complex in the sense of this definition. So every complex manifold, usual complex manifold, is almost complex. I will use this abbreviation, almost complex, okay? AC. Well, why that, by the way? Well, suppose that you have a complex manifold M, is a usual complex manifold. So you have standard atlas with cards, and the transformation maps are usual biholomorphic maps. So the picture is something like this. So you have two cards. That would be the chart U and U prime. And you have here local coordinates Z. And you have here local coordinates Z prime. And Z is a diffeomorphism from U to some subdomain G of Cn with the standard structure, right? Because this is usual complex manifold. And this is a diffeomorphism to some domain G prime in Cn, also with standard complex structure, right? So then we can define an almost complex structure on the whole manifold M as follows. So we said our almost structure is defined on U as follows. We consider the pullback of the standard structure by Z, by the diffeomorphism Z. So this is Z star of this. In other words, this is this. Okay? So it's very easy to see that this defines an almost complex structure on U. Now, if we would like to check that the definition is correct, we have to check what? If we consider on the intersection an almost complex structure which is defined by means U prime by the similar rule, then they coincide. And this is obviously true because the transformation map are biholomorphic with respect to the standard structure on Cn. And I leave it as an easy exercise. Are biholomorphic in Cn J structure. So the definition is correct. And using this, we obtain an almost complex structure which is globally defined on a complex manifold M. Okay? So in particular, every complex manifold is orientable because every almost complex manifold is orientable since tangent space, every tangent space has a canonical orientation. Okay, so a word about local representation. Local representation of almost complex structures. Suppose that we have point P in M, J, and we have local coordinates Z. Well, such that Z of P is equal to 0, and we can transport, here we have the structure J, we can transport it by Z on Cn. So we consider the direct image of Z, of J, which is defined by And this is an almost complex structure here. This is, okay, you can see, consider, let it be the unit ball, in Cn, if you want, okay? So this is almost complex structure which lives here. And with some abuse of notation, I also will denote it by J. So you can view it as a coordinate representation of J. So let me denote it by J. So let us denote it by J with some abuse of notation. Then you have, so then our structure J lives here. Because anyway, if you denote it, say, by J prime, then this map Z will be Bach holomorphic map between these two almost complex manifolds in the sense of definition which I introduced before. So if you do complex analysis here, you can do it here, everything will be canonically isomorphic, okay? So in order to avoid complication of notation, I denote this transported structure here by J, and so what J represents? J is a tensor field on the open piece of Cn. So you can view J as a matrix-valued function. J, if I denote here the coordinates by Z, so J to every point Z of the ball associates J of Z, which is a real endomorphism of R to N. So this is just a matrix, right? So this is an element of M to NR. So this is just a matrix-valued function. The value is a real 2n times 2n matrix, satisfying this condition. This is negative identity matrix at every point Z. So this is exactly a local representation of almost complex structure as a matrix-valued function. And if you, well, moreover, if you are in the origin, as we know, if we consider here the tangent space, there is a linear transformation of this tangent space such that after this transformation, at the origin, our matrix becomes equal to the standard structure, right? So you always can suppose, after additional linear transformation at the origin, that J at the origin is equal to J standard. So so this means that the value at the origin of your matrix function is equal to this constant matrix for standard structure, which I wrote at the beginning, right? So you always can achieve it by additional real transformation. Well, now near this, there is a very simple but very useful trick for applications. What happens if we consider smaller and smaller neighborhoods of zero and if we blow up it by isotropic dilations of coordinates? Namely, so isotropic dilations. Isotropic dilations. For every positive epsilon, let us consider the map d epsilon z, which is equal epsilon negative 1 z. This is just usual multiplication. This is a linear map. Now let us consider, okay, I have my structure J, which is here, right? Let us consider the direct image of our structure J by this family of maps. So I say, I put J epsilon is equal, by definition, by d epsilon star of J. So this is d epsilon, well, I do not write here a differential because this map is linear, okay? So in principle, I have to write tangent map, of course, at every point. Well, it is linear. Okay, so what we can say about this family of structures? Observation is very simple. For every compact subset K of Cn, this family of structures, J epsilon, tends to the standard structure J standard on this compact subset in any CL norm when epsilon tends to 0. So for every L. big enough, well, from C1 or something like this. So this means that our family of structures, J epsilon, becomes closer and closer to the standard one in any norm. So geometrically, if you consider this neighborhood, and you blow up it by isotropic dilation, then, and you blow up your structure, then you obtain a structure which is closer and closer to the standard one, together with all derivatives. And this is very simple, it's very easy to check it, so I leave it as an exercise. This is trivial computation in coordinates. This is a source of some deep results. Local existence theorem for complex curve, for instance. Okay, so by the way, what are J-complex curves now? So the next subject is J-complex curves. Suppose that we have, so S is a Riemann surface. Well, so a Riemann surface is just a one-dimensional complex manifold, right? So in particular, this is an almost complex manifold because every complex manifold is almost complex. So I can write like this. SGS, this is an almost complex structure which is canonically defined on the Riemann surface by the construction which I explained there. Okay? So we have an almost complex structure, an almost complex structure here, and we consider a map F to some almost complex manifold M. If this map is holomorphic with respect to these two structures, then we say that this is a J-complex curve. Okay? So if this map is holomorphic, in the sense of definition which I introduced, then we say that it is, then we say that that this is F is a parametrized J-complex curve. Well, this is standard abuse of notation. Parameterized complex curves are not sets. This is maps. They're maps. Okay. Well, this definition is a little bit, well, maybe, well, it is precise, but there are two important special cases which will play important role in the theory. The first special case is when S is the unit disk of C, of course, with the standard structure of the complex plane. So S, I will always use this notation for the unit disk. And always the structure will be standard if I did not mention the opposite, so structure is standard. So in this case, F is, so this map, once again, is called, there are several absolutely equivalent ways to call it. So J-complex disk, J-holomorphic disk, well, what else? Pseudo-holomorphic disk, and so on. By the way, here also, instead of J-complex curves, in the literature you can meet pseudo-holomorphic curves, J-holomorphic curves, all this is the same, okay? So this is just our basic definition. So this is first important case. And the second important case is when you have here the Riemann sphere. So S is the Riemann sphere. So then F is called a J-complex sphere or J-holomorphic sphere. So F is called a J-complex sphere in M. Okay, and probably the last word about non-parametrized. So non-parametrized curves. This is the end of that definition. What's obvious? So if we have a x in M, J, a real surface, so we call it a non-parametrized J complex curve. If locally it can be parametrized by a disk, for instance, if for every p of x there exists a neighborhood u of p such that x intersect with u is the image of a J complex disk. Well, my definition is not the best possible because when I say real surface, I suppose, in principle, I have to suppose that this is a smooth real manifold. Well, maybe we can assume in this definition that there are some singular points and so on. So I do not develop this subject. I will discuss it a little bit later. Okay, this is not very important at the present. So from now on, I mostly will work with parametrized curves. So basically, a big part of Gromov theory is about maps and not about sets. It is much more difficult in some sense to develop a similar theory for sets. For instance, compactness theorem in the best form are proved only for maps. Okay, so we will mainly working with parametrized curves, in fact, so with maps. Okay, so this is the end of this definition. So now, how to do analysis with this object? We need some analogs of Cauchy-Riemann equations, and so this is the next step. So Cauchy-Riemann equations, Cauchy-Riemann equations for a J complex disk. So I suppose now that everything is local. So locally, I can identify, so I have Mj, and I identify it, so we identify with the unit ball in Cn, for instance, where we have this matrix-valued function J, okay, as I explained before. So in that situation. So in principle, we have, and so we have local coordinates, and we have a disk. So I use this notation with some standard abusive notation. Z are local global coordinates in Cn, and also the map will be denoted like this. So Z to average zeta of the unit disk, Z associates Z of zeta, which is in the unit ball, and we consider this map, which is a J complex disk. So it satisfies this canonical definition of this definition, in fact. It satisfies this definition. Well, now a direct computation in coordinates, which uses the assumption, which uses this property of almost complex structure, this property, and I leave it as exercise, shows that the fact that this map is J complex is equivalent to the following system of PDE equations. So perform this computation, it is useful. So system is the following. Z zeta bar, negative A of Z, Z bar zeta bar is equal to 0. And this system of equations we will call the Cauchy-Riemann equations for the almost complex structure J. So that I will refer this like this, CR. This is the main object of the theory, in fact. Well, let us think a little bit what it is and what it represents. Well, what is A, first of all? And how A is related to J, to our almost complex structure. So J is essentially this matrix valued function, right? J associates to every point Z of Cn a matrix 2n times 2n real matrix, right? So how A arises? In fact, A arises as follows. We can consider L, which is in fact this real endomorphism. It's very easy to show that the condition J square is equal to negative identity implies that this real linear map L is C-bar linear, anti-C linear. So the action of L of every vector V of Cn can be written like this. This is multiplication by matrix A and the conjugation of Z in complex coordinates. Okay? Here I view, I'm sorry, this is Z, this is V. Of course. So here I view V as a vector of R2n, L as linear operator which acts on V, but the result can be written in this form where A is complex n times n matrix. Okay, so this matrix can be canonically restored from J essentially by this formula. Of course, when I apply this formula, I need some assumptions. For instance, I need that this matrix is invertible, right? So this means that, for instance, the operator norm of J must be smaller than 1 or something like this. This is not a big problem because if our considerations are local, then we can suppose that in this ball, our J is very close to the standard matrix and so on and so on. So everything works because we consider, so for instance, this will be very close to the 0 and so on because we can consider isotropic dilations of coordinates, which I explained before, and everything will work. So it will be invertible and it will work. Okay? So everything will be defined. What is important, in fact, one can restore, it is less obvious that one can restore J from A. It is even possible to write an explicit formula using some a little bit more advanced tools of linear algebra. I will not do it, but locally, the conclusion is that locally there is one-to-one correspondence between J and A. And so in the general Kodaira theory of deformations of complex structures, A often is called the deformation tensor of an almost complex structure, so the deformation tensor. Well, I do not like this terminology because it is a little bit intimidating and so on. So I always use it, call it complex matrix of J. Okay, so the complex matrix of J. And important thing, of course, A is not an intrinsic object in some sense. It depends on the choice of local coordinates. J is an intrinsic object. It is an almost complex structure, which is a tensor field and so on. A, of course, depends on chosen system of coordinates. So if you change the system of coordinates, you will change A. And in fact, for instance, in many applications, technically, it is important to have the relation between A and A prime if A prime is this matrix associated to another system of coordinates. Okay, so now if Z prime is another local chart and A prime is the complex matrix, is the complex matrix of J in these coordinates. So then The relation between A and A prime is the following. This is also an amazing exercise. I write because I am not able to memorize this formula, in fact. So this is like this. This is the formula, which allows to recompute a new complex matrix if you know the old one, and so on. Okay? Well, the main analytic tool in the theory is the Cauchy-Green integral. So the Cauchy-Green integral. Well, I will use a similar notation to which is similar to the notation of Sergei, but maybe just slightly different. So T omega of F is equal to this. Of course, this integral, well, omega is a domain in C. Well, when omega is equal to the unit disk, I drop the index, so I write just like this. Okay. Well, as Sergei told during the first lecture, the very important property of this operator is that this is a smoothing operator. It increases the smoothness if you consider it in Herder classes. In other words, T from Ck alpha d to Ck plus 1 alpha d is a linear continuous operator, is a bounded linear operator when alpha is not equal to 0, of course. This is important. If not, it is not true. Okay, and what is very important, this is a solution of the d-bar equation of the unit disk. That is, d zeta bar of t is equal to the identity. Right? So this is two fundamental properties of this integral which we need now. Okay, so now we can prove the local existence of J-complex curve, because it is not quite obvious thing. In the case of the standard structure, it is clear that you have a lot of solutions of Cauchy-Riemann equations. Oh, by the way, why we call these equations Cauchy-Riemann equations? Maybe I'm going too fast. If J, probably you have observed it. Let us go back here. If our structure J is equal to the standard one everywhere, what happens with our system? So this matrix will be 0, because L will be 0, and so this associated matrix will be 0. So we obtain just usual Cauchy-Riemann equations, right? So this system of equations is precisely a generalization of the usual system of Cauchy-Riemann equations for a map from the complex plane to Cn, for instance. Okay? So you can view it as some deformation of the standard system of the Cauchy-Riemann equations. This is not a linear system, and this is a difference with respect to the standard theory, because this is just a quasi-linear system of partial differential equations, because A depends on Z. Z is dependent variable, right? Zeta is independent. So this is quasi-linear system of partial differential equations, and when A is small, it is quite easy to see that this is elliptic system. I do not think too much about this, but in fact, it is very important that, from general point of view, that you still have ellipticity condition for J-complex curve. This explains a lot of phenomena which will occur in this theory, in our courses. Okay, so this is just a suitable generalization of usual Cauchy-Riemann equations. And the Gromov theory, all Gromov theory from the PDE point of view, is just the theory of solutions of this system of equations. and nothing else. Okay? Of course, this system, it is obviously that I simplify a little bit, because this is written locally, right? If you have an almost complex manifold, you cannot choose a local chart along your disk, right? Because maybe the image of your disk is very big and it can be covered by family of cards. But you cannot, in general, you cannot choose a unique chart such that you have this representation, right? So in principle, in the general situation, you cannot write explicitly this system of equations. But nevertheless, Gromov theory is about this. About these equations, which can be viewed more geometrically in the more general situation, but this is about this. Okay? Well, so now, why the solutions of this system exist at least locally? Okay? When you have a good chart and so on. It's easy to prove it. If we consider now using this operator T, we can replace this by the following. So this expression z zeta bar minus a of z bar zeta bar can be written like this. So this is z minus t a of z bar z bar zeta bar, right? This means that this is equal to, we can write this operator exactly is equal to this one, because z zeta bar and zeta bar of t is equal to identity, right? So when we take the derivative, we obtain exactly this one, right? So our system of equation can be written like this. This is equal to 0. So this means that this expression is just a usual holomorphic function, right? So this is equivalent to this equation. Is equal to h, where h is a usual holomorphic function in the unit disk. So h is a holomorphic map from D, usual holomorphic map, because this is a solution of the usual D bar equation. Well, so now what we would like to do, how to construct solution of this equation. We would like to fix h and solve this equation with respect to z. It is absolutely obvious that we always can do it. And in fact, there is a theorem about this, so which is called Neuenhuis-Wolff theorem in Annals of Mathematics X in 63, which general statement is the following. For every point P of an almost complex manifold, and for every tangent vector V at this point, there exists a holomorphic disk, so a J-complex disk, with the center at this point, that is f of 0 is equal to P, and with the tangent map, the tangent direction, so the image of this vector is equal to lambda v for some lambda which is positive. So the direction of the tangent vector at the center of this disk is proportional to this v. Well, the proof is absolutely obvious, in fact. So the proof consider here on the left hand of this equality. If we consider the operator which to every z, every smooth map z of class ck alpha associate this expression, this is the map to what? Z is ck alpha. So z bar zeta bar is ck minus 1 alpha. But t increases the regularity. So this is again expression which is of class ck alpha, right? So when the norm of this matrix is very small, and we can assume that the norm of this matrix is very small when everything is local using isotropic dilations. Because when everything is local, then J is very close to the J standard, and all this is very small, and so A is very small, and so the norm of A is very small. So this operator, which to Z associates Z minus TA of Z, Z bar zeta, this is a nonlinear operator, which is invertible, of course. This is invertible operator simply by the implicit function theorem. So now we fix H, and we consider the inverse operator, and we obtain the solution of this equation, which roughly speaking means that locally you have precisely the same quantity of J-complex disks as usual holomorphic disks. There is 1-to-1 correspondence between usual holomorphic disks and J-complex disks if you consider your situation locally. This is obvious consequence of the implicit function theorem, and this is precisely the same proof as the proof of Cauchy-Lipschitz theorem for existence and uniqueness of the solutions of systems of ordinary differential equations. But instead of the usual integral, as in Cauchy-Lipschitz theorem, we use this integral, which fortunately has similar properties. It improves regularity in all variables, and everything works in quite similar way. So this is Neuenhuis-Wolff theorem, which is just application of the implicit function theorem. Well, so locally, there are no problems. J-complex curves always exist locally. And this is, in fact, a good news, because you will see that with other objects of usual complex analysis, the situation is not so good, in fact. OK, well, now, a couple of examples. So examples. So let everything will be in dimension 2. Okay? The dimension is 2, and everything is local. So we have our almost complex manifold J of complex dimension 2. We consider some point P, and locally by this, well, by the way, I forgot to say, well, it's absolutely obvious by the implicit function theorem. If you perturb here the structure J of, if you, this is not this theorem, I'm sorry. If Neuenhuis-Wolff theorem, if you perturb your tangent vector, or you perturb a point, or you perturb a structure, the solution of our equation will depend continuously on this perturbation by the implicit function theorem. So this theorem allows construct not only single disk, but family of disks, and so on, which depends continuously on parameters, and so on. So this is just the implicit function theorem. And this is very convenient locally, because in dimension 2, we can consider the following. We consider here a one parameter family of J complex disks. I denote them like this, GZ of D. So this is the disk, and Z runs over some open subset of D. This is complex one parameter family of disks. I can consider again by Neuenhuis-Wolff theorem, I can construct a transverse family which also foliates this neighborhood. Let me denote it by HW of D. This is image of every disk, and W also runs over C. Well, then for every point P here, there exists a unique Z such that this point belongs to this disk, and unique point W such that this point belongs to this to the disk of this family. So ZW is a local system of coordinates, of curvilinear coordinates, right? Is a local system of coordinates. And this piece of your manifold is mapped on an open piece of C2. And in C2, if you transport your almost complex structure, you obtain here an almost complex structure J such that the coordinates line a J-complex curve by construction, because this was complex disk, right? They're non-parameterized. And it is interesting to write the complex matrix of our structure J in this system of coordinates. The matrix will be like this. It will be diagonal. Exercise. Check it. The matrix will be like this, precisely. So you always can do it. You always can diagonalize in a suitable system of coordinates the complex matrix of your almost complex structure. So it allows to simplify the Cauchy-Riemann equations for J-complex disk, which helps a lot in many considerations, in fact. In fact, the basic idea, if you locally study these nonlinear Cauchy-Riemann equations, of course, the main analytic idea is to try to simplify these equations by a suitable change of coordinates in order to make it as close to the standard Cauchy-Riemann equations as we can. Unfortunately, it is impossible to linearize them completely. And this is, in fact, the main subject of my lecture today. OK, so you obtain here this thing. And in the second situation, this is the second very typical situation. And the first one. And the second one is, if you consider a single disk, f of d, which is J-complex, and you consider a transverse family of J-complex disks, geometrically situation which we meet very often. So this is J-complex disks, Hz of d, which are transverse to f of d, and you can show this in such a way that at the origin, every disk is like this. Then you can parameterize the neighborhood of f of d by this map. H of zw is equal to hz of w, and h is the map from the bidisk to this neighborhood u. If your map f is embedding, then you can choose h embedding. If not, you can choose h as an immersion. And then you can, here you have structure J, and then you have here the bidisk. You have H, and then you can consider the pullback of J on the bidisk. So here you have this H star of J, so which is dH negative 1 J dH, right? And if you consider here the complex structure, the complex matrix of this structure, it will be like this. A, B, 0, 0. So the right column will be 0, exactly. And this also helps a lot in suitable consideration and in suitable analysis of disks. Here the curves are parameterized. And in fact, the zero section here, W equal to 0, corresponds to this disk, and it will be a true J-complex disk. So this means that this matrix A vanishes along the axis Z. So when A and B vanishes when W is equal to 0. ZW are coordinates here, right? Okay. Well, so now we pass to the following fundamental notion: integrability of almost complex structures. For integrability, enormous complex structure J is called integrable if for every point P in M there exists a neighborhood U of P and the local and the chart, so Z from U to the ball of Cn such that J is equal J on U is equal to the pullback of the standard structure by Z. Okay. So analytically, this means the consequence is very simple. This means what? This means that if the structure is integrable, then in the neighborhood of every point of your manifold, you can perform such a change of local coordinates such that in the Cauchy-Riemann equations, A will disappear. So the Cauchy-Riemann equations will be usual linear Cauchy-Riemann equations for holomorphic disks. So you can linearize your system of Cauchy-Riemann equations in the neighborhood of every point. So this means, roughly speaking, that your system is integrable. And if every almost complex structure is integrable, then you do not need all this because there is a much better situation is much better. You can perform a suitable change of coordinates such that A will be 0 in a suitable system of coordinates. Well, unfortunately, in general, this is not true. And there are almost complex structures which are not integrable. And moreover, in fact, it's very rare for an almost complex structure to be integrable. Generically, they are not integrable. This is a very important thing. Okay, let us see why. And this will be the end of my lecture for today, in fact. Okay, so if, by the way, from the definition of almost complex structure on a complex manifold, we obtain that if your almost complex structure is integrable, this means that your almost complex manifold is a usual complex manifold, right? It's exactly usual complex manifold. Well, okay, so let us understand a little bit more this notion. So we need the notion of formal integrability. Formal integrability. Let me explain a little bit what it is. So first of all, let V is a complex vector space. Then I can consider on V. So first I consider V as a real vector space. Okay, then I consider the dual space. I tensor it with C. And this simply what? This is the space of all. So R linear forms from V to C. So this is C-valued R linear forms, and it is very well known that you can decompose it as a direct sum. So this is C-linear forms, and this is anti-C-linear forms. C-linear forms, this is anti-C-linear forms. So, and this okay, maybe it's better to write it. Okay, let it be like this. And so if we apply this construction on every cotangent space to our almost complex manifold, then we have this decomposition. We obtain that the space of one forms with complex coefficients can be decomposed like this on M. So this is C-linear form, this is anti-C-linear form with respect to our structure J. And so we can consider the exterior product, and then we contain PQ forms. All this is very standard, PQ forms, okay, which every PQ form contains P exterior products of these forms and Q exterior products of this form. So this is lambda PQM, okay. And so definition of formal integrability is the following. So J is called formally integrable if for every form of type 1, 0, its exterior derivative contains, does not contain zero two terms. Well, obviously, obvious claim. If your almost complex structure is integrable, then it is formally integrable. Well, this is obvious because the standard complex structure is, of course, formally integrable, right? So integrable, so J is integrable, implies formally integrable. Well, because this notion is essentially local, it suffices to check it in the neighborhood of every point. And if your structure is integrable, that in the neighborhood of every point, it is bar holomorphic to the standard structure. And standard structure is, of course, formally integrable. If you consider any PQ form, you take exterior derivative. If you consider any 1-0 form and you take exterior derivative, there are no 0-2 terms when you consider the standard structure. So to be formally integrable is necessary condition in order to be integrable. And this condition is sufficient, and this is much more difficult, and this is Nylander-Nirenberg theorem. Okay? So fundamental theorem, and this is much harder than Nine-Hughes-Wolff. So theorem, Nylander-Nirenberg. So J is, if J is formally integrable, then J is integrable. Well, before proceed the idea of the proof, let me first state a very convenient criterion how to check the formal integrability condition in practice. In fact, it is not difficult. So locally, let alpha 1, alpha n is a complex dimension of manifold, let it be a basis of 1-0 forms. Then J is formally integrable if and only if this condition holds d alpha j, exterior product alpha 1, etc., alpha n is equal to 0 for all j. This is obvious, in fact, so I leave it for exercise, as an exercise. Okay? It is much more convenient than the general definition, nevertheless, because in the general definition, you need to check something for every 1-0 form. And here you need to check something just for finite number of forms, which in local coordinates always can be explicitly written. So if you want to write explicitly this condition, this is very convenient, in fact. And this is very convenient criterion. OK, so now, keeping it in mind, let us proceed a proof of this theorem. Well, I proceed to the proof just in two special cases, n equal to 1 and in n equal to 2. In n equal to 1, essentially, it was proved in the first lecture by Sergey. And let us understand why. It is amazing. OK, so first case, let dimension be equal to 1. Okay. So in this case, what means that our almost complex structure is formally integrable? There is just one form of type 1-0. I suppose that everything is local. So we are near the origin. The structure J is very close to the standard one because we always can do it by dilations and so on. So everything is purely local. So locally, everything is very local. Okay. So then alpha, just one form, can be written like this. It must be small deformation of the 1-0 form for the standard structure, right? So it must be something like this, right? And nothing else, where A is some smooth function which is very small. A is the complex matrix of our structure in this case, because in dimension 1, our complex 1 times 1 matrix will be a function, essentially, right? So this is our capital A, essentially, right? So we have this form, and so now if we have a map F from the disk with the standard structure to our manifold, to our C with this structure, which is J complex, then our Cauchy-Riemann equations for this complex disk will be like this. It will be f zeta bar minus A of f bar zeta bar is equal to 0. So this is our Cauchy-Riemann equations, right, for this case. Well, and now applying the argument, well, I forgot to say, this condition holds trivially, right? So our structure, of course, is formally integrable. So it is so J is formally integrable. So in complex dimension 1, any almost complex structure is automatically formally integrable, right? So now you consider this equation and you solve it by the implicit function theorem using the Cauchy-Green operator, as I did in the proof of Neuenhuis-Wolff theorem, and we are done. So I replace this by this equation. Is equal to H, where H is a usual holomorphic. And this is an invertible operator because A is very small. And for instance, as H, I take, so choose H of zeta is equal to zeta. And then when A is small, F will be small deformation of this map. So it will be local diffeomorphism, right? And so it is done. We obtain that we can parameterize our neighborhood by a complex disk, so which in complex dimension 1 is the answer. Well, but what is the relation with the lecture of Sergey today? The relation is very simple. If we consider the inverse map from this to this, then it will be solution of Beltrami equation. Why that? So now, if you consider now G, right, the map from Cj to, I don't know, C with the standard complex structure, and this map is holomorphic with respect to these two structures. holomorphic. Well, we can write, of course, this general definition with commutativity relation and so on, but it is a little bit complicated. In order to traduce this condition of holomorphicity to the language of equations, it is better to observe that this means what? This means that the pullback of every 1-0 form here must be 1-0 form, right? If our map is holomorphic. Okay, what is 1-0 form here? This is d zeta, for instance, what notation I use. Okay, d zeta, okay? So this means that J star of d zeta must be this form, but with respect to this structure, right? Okay. So this means what? What is this form? You just compute the pullback. So this is this. And so since this form is the basis in the space of 1-0 form, so this must be proportional to this form. It must be equal to P alpha, right? So it must be equal to P dz minus P I over z dz bar, and so we obtain that gz is equal to P, and g zeta bar is equal to negative P a z. And now we exclude P from this system of equations, and this is equivalent to the equation z g zeta bar plus a of z g z is equal to 0, right? And this is precisely the Beltrami equation. The only difference with respect to this is that the sign, right? But in fact, this two, so the inverse map satisfies the Beltrami equation, right? But in fact, please notice that these two equations are of totally different nature, in fact. The Beltrami equation is linear because here z is the independent variable. This is a linear equation, and this is very natural because when here, in the target manifold, when your structure is standard, then the sum of two holomorphic maps will be holomorphic map and so on. This equation looks similarly, but it is not linear, right? It is just quasi-linear because f is dependent variable, right? So this resolution of these two equations is very similar by the Cauchy-Green operator, but these equations are of very different nature, right? Well, so okay, so in one-dimensional situation, everything is clear. So what in dimension 2? And you will see that here the situation is substantially more complicated. So I will prove the theorem just in dimension 2. But the general idea is totally similar. I will start at last the proof. So case n equal to 2. So first of all, everything is local, so I can suppose that the complex matrix of my structure is diagonal, as I explained. We can simplify A considering the coordinates given by two transverse foliations by J complex disk, which exists by Neuenhuis-Wolff theorem, right? So I suppose that my matrix is like this, and it is not a problem. We always can reduce everything to this. Well, then the Cauchy-Riemann equations will be. So if I will use the following coordinates. So ZW in C2 are standard coordinates. Standard coordinates. Well, so then if you have a map from the unit disk which is J complex, then the Cauchy-Riemann equations will be written in this form. So in fact, in some sense, you can separate this system splits on two systems, but we take care because A and B depends on ZW. So it splits with respect to derivatives, but not completely, right? Because A and B are functions of Z and W, right? We can split it on two completely independent systems, nevertheless. Okay, so we have this. Now we would like to write the condition of formal integrability. In order to do it, we have to write a basis of 1-0 forms, and as an exercise, prove that you can write it as follows. This so basis of 1-0 forms with precisely the same A, B, which are here. Precisely with precisely the same. Right? Okay, this exercise, check it. When you have this, we apply our criterion. So you write this condition that d alpha 1 wedge product with alpha 1 alpha 2 is equal to 0, and so on. You compute what you have, and you will have integrability conditions. Which are the following? AW bar plus B, AW is equal to 0, and BZ bar plus A, B, Z is equal to 0. So this is precisely two integrability conditions on the coefficients of our systems. Well, now what does it mean that our system, that our complex structure J is integrable? This means that there exists a holomorphic map from an open neighborhood of C2 with the standard structure to a neighborhood of C2 with this structure J, right? Which is biholomorphic with respect to these two structures, right? This means that our structure is integrable. So what does it mean that this map is holomorphic? So now, if we have, now I use the following notation. So now let zeta 1, zeta 2 be coordinates in C2, and suppose that we have a map. So this is still zeta. And suppose that we have a map which takes this to Z of zeta, W of zeta. This map is J standard, J holomorphic. If and only if it still satisfies, let me denote this system by 1 to 1. But the only thing, of course, we have to explain what we mean by Z zeta bar, Z W bar. Here we use the following notation. Z zeta bar is the line Z zeta bar 1, Z zeta bar 2, and W zeta bar is equal W Z bar 1, W Z bar 2. So in fact, here you have 2 times 2 matrix, right? And here similarly, you have 2 times 2 matrix. And so this is equality, not vectors, but 2 times 2 matrix, right? Matrices, right? So if you use this notation, the system will be precisely the same. Can be written in precisely the same form. Okay, and now we have to produce the solutions of these systems, of the system under the assumption that we have these compatibility conditions. And in order to solve this system, we have to solve in some way the D-bar problem for the standard Cauchy-Riemann operator in the bidisk. So maybe I will continue next time, because this is a good opportunity to step. Okay, so I do it. Okay, thank you.